opportunity. At the same time, no, we are also recording this program, which will be made available on our NDL, that is National Digital Library. The entire program will be available. So this is information for all the participants, that you may be knowing few other colleagues, friends who could not participate in this program because of the schedule constraint. So later on also this program, no, of course, after a month time, this program will be made available on NDL through the national coordinator of the program, Professor Anil Agrawal from IIT Hyderabad. So with this, I conclude here. Thank you very much, and I congratulate both the organizers, Dipayan Guha and other PI, for hosting this program. Thank you very much. Wish you all the best.
Thank you, sir. Now I request our foreign experts, Professor Hamid Raza Karimi, to share his thoughts about the course.
Okay, so thank you very much. Good afternoon, everyone. So first of all, it's my pleasure to have this opportunity for the first time to collaborate with the University of the Motilal Nehru National Institute of Technology in Allahabad. And in my role, I would like to thank the National GiAN Course Coordinator and also the local GiAN Course Coordinator, and also the head of the department, and of course the principal course coordinator, Dr. Guha. So my name is Hamid Raza Karimi. I'm from the Department of Mechanical Engineering, Politecnico di Milano. So as I mentioned before, that the topic of the course addresses two keywords about the resiliency and also the cyber physical system. And as also the National GiAN Course Coordinator, he mentioned that we are looking at some emerging topic in terms of technology and also from the methodology aspects. And the topic of the course proposed to this association after the very deep discussion with the Department of the Electrical Engineering at the MNNITA University. So we came up to this important topic about this resiliency for CPS. So because I'm serving as the editor-in-chief for the Journal of Cyber Physical Systems, and I have been familiar with the research ongoing in this area in India. So that's it in the whole country in India. So the topic of the CPS is a very hot topic, and I'm familiar with this aspect. And after reading a lot of articles produced from your country, I came up to some important issues we need to address in the course. So one is about the foundation and the fundamental aspects. So on the CPS, on the network-based control, and also coming to look at the resiliency and control. So that's it. As also the other colleagues they mentioned. So we are looking at to address some research gap from the teaching aspect and also from the technology aspects. And I hope during this 5 days course, and thanks to my colleague, Dr. Dipayan Guha, so we have scheduled some topics. And first of all, it was my pleasure to be giving this course online, but as you know that, in fact, we are expecting to give this course in presence. But during to some constraint in the schedule, and then we move to the online teaching part. But of course, if this course want to be repeated, I would be happy in the future to travel to India and also. So during the course, I hope you could be very interactive discussion with all the participants. And as also Dr. Guha, he mentioned that the course has received a good number of the registration, and I'm very happy to hear this news. And as based on my teaching style and the research style, so I hope that this course should be one basis for the future collaboration between the other universities, and also to extend the collaboration from Politecnico Milan in Italy to the whole country in India. So, of course, I have a long collaboration with India in different universities, but I know that it's a large country and also with a high potential in the research. And I hope that this teaching material will be offered during this 5 days course. Could be a good start to get know better each other, and also which I try to introduce some key research topics during the presentation of the course. And I would always accept all the comments, any questions. So please feel free to contact me anytime by email and also during the course. And I hope this kind of the interactive discussion during the course could give benefit to all of us. And this is one of my objective from the outcome of this course. And again, thanks to all the colleagues and the national coordinator for giving this opportunity. And I hope this could be a good start for the future and the long-term collaboration between Italy and also India. Thank you very much.
Thank you.
Thank you, sir, for your kind words. Now I request our Honorable Director, sir, to kindly deliver his presidential address to the participants. Sir, your voice is not audible, sir.
Sir is muted. Sir,
your mic is off. Sir, your mic is off. Sir, your mic is off.
Dr. Dipayan, I request you to send some student with a device to sir's office if it is convenient for you.
Okay. Can you hear me now?
Yes, sir, it is coming. The voice is low, sir. Your voice is coming, sir, but it is low, sir.
Can you hear me? Fine with my
Dr. Dipayan, would you like to
Yes,
send
sir.
someone with a device? Maybe a mobile will be
Sir, I
helpful.
have asked my students
Yeah, that's
to.
great. Yeah, thank you.
Yeah, I have asked my
Should be
students.
fine. So what a device need to be sent? Yeah.
Yeah.
Now you can hear me?
Yes, sir.
Yes,
Yes,
sir.
sir. It is audible.
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. First of all, I'd like to thanks Electrical Department for organizing this GiAN course, which is a very important topic on the cyber surveillance. And also, I'd like to welcome on behalf of the MNNITA, Dr. Raja from Italy, who is kind enough to accept our department invitation to be with us for 1 week, delivering a lot of lectures during 1 week in this conference. I think I also welcome Dr. Maiti from Shivpur, who is an internal expert in this program. And when I went to this conference material, I found is very interesting because this is a very, very important topic these days, because everyone they want to secure the data and in a physical form also, not only the other forms. So I don't think that all the industries and all the academic need to have these kind of programs and this kind of knowledge in their one. And I believe that this course, 5 days week, will help us, the faculty and students of NIT among the various NITs in India, and also the students of MNNIT here. So I'm also thankful to our local GiAN coordinator, Dr. Sahu, who is a very, very enthusiastic to have this kind of program as academic excellence in our institution also. So I wish all the success, and I would like to say one thing. Please ask the question with the experts. Whatever doubts you have, is he already told that you can reach to him by email, or you during the lecture also you can ask the questions. So once again, I congratulate the Department of Electrical Engineering, especially Dipayan Guha, other people for conducting this course, and whatever required to do that thing, please let me know. I'll be very helpful to that. I wish you could do it here online, offline. Dr. Hamid would have been much better, but unfortunately due to lack of time or maybe your busy schedule, you were not able to make it here. But maybe next time, whenever this kind of program comes, please do visit MNNIT here. And also Dr. Maiti also, who is an Indian expert on this topic. Once again, I wish you all the success of this program in next 5 days. Thank you very much.
Thank you, sir. Thank you for your continuous guidance, which motivated us to pursue this excellence in this emerging field of control theory and make this GiAN course successful. Now I request Dr. Arvind Kumar Prajapati to place a vote of thanks before the House.
Thank you, sir. Honorable Director, sir, National and Institute Coordinator of GiAN, Head of the Department, Foreign Expert of the course, Principal Course Coordinator, faculty members, and dear participants. Good afternoon to one and all. It is a privilege and an honor to place the vote of thanks at the inaugural function of the One Big GiAN course on resilient control of cyber physical systems, scheduled from March 24 to 28. I, Dr. Arvind Kumar Prajapati, Assistant Professor in Electrical Engineering Department, MNNIT, Allahabad, extend my heartfelt gratitude to everyone who has contributed to making this event a grand success. First and foremost, I would like to sincerely thank our Honorable Director, Professor Ramasankar Verma sir, for gracing this occasion with his esteemed presence and support extended to us for making this GiAN course successful. Sir, your continuous guidance helped, inspired, and motivated us to pursue excellence in the emerging fields of control theory and cyber resilience. I sincerely thanks to the National GiAN Coordinator, Dr. Anil Agrawal sir, IIT Hyderabad, and the Institute GiAN Coordinator, Professor G.P. Sahu sir, for their unwavering support and guidance in the every endeavor of our GiAN course. I sincerely thanks to our head of the department, Professor Richa Negi ma'am, and in charge head, Dr. Deepak Kumar sir, for your valuable support, guidance, and encouragement in every endeavor of this course. I extend my sincere gratitude to the foreign expert of the course, Professor Hamid Reza Karimi sir, who has consistently reviewed the progress of the course and guided in preparing modules, lecture, tutorials seamlessly. Sir, it is our honor and privilege that you have accepted our request and actively participated in the course. Your vast experience in the control theory, computing, and cyber resilience will encourage and open research paths for all the learners in the respective field to pursue their sustainable research. Thanks to our principal course coordinator, Dr. Dipain Guha sir, and course coordinator, Dr. Sordeep De sir, for their continuous efforts, dedication, and coordination in structuring and executing this GiAN course. I sincerely thank all the faculty members of the department who have mentored and supported in organizing this event. Your constant encouragement and guidance ensure the smooth functioning of our activities. I also want to acknowledge our student volunteers' hard work and dedication, who have worked tirelessly behind the scenes. Your energy, curiosity drive this department to organize events that contribute to professional and personal growth. From planning to execution, your efforts have ensured that today's event was a grand success. I also want to thank our participants for showing keen interest in this course and encouraging them to interact actively with our foreign expert during the course. Last but not least, I extend my gratitude to our sponsor and collaborators, GiAN, the Ministry of Education and Government of India, who have supported us in making this event possible. GiAN Office, IIT Hyderabad, for extending all supports starting from the proposal submission. The speaker in this workshop are from different reputed institutes. They are experts in the field aligned with this GiAN course. Attending their sessions guaranteed that your next 5 days will be delightful and memorable. Thank you for being a part of this course. Thanks to our department staff also for their support. Thank you once again for the joining of the inaugural function and making this event memorable. Wishing you all a wonderful day ahead. Thank you. Thank you very much.
Thank you, Dr. Prajapati. Now I request the patron of this course and Honorable Director, sir, to kindly announce this course officially open. So I request Honorable Director, sir, and patron of this course to please announce this course officially open.
Okay, the privilege given to me as a director of MNNITA, I announce this program should be open.
Thank you, sir. So with this, we are concluding the inaugural functions of 5-day GiAN program. And I request Professor Hamid Reza Karimi sir to please start his sessions. The participants, you are requested to be here in the same virtual platforms. So the session is going to start immediately. And
with your permission, can I leave?
Yeah, please, sir. Thank you, sir. Thank you, sir.
Thank you, Professor Kazmi.
Thank you very much, sir.
Hamid Reza, thank you so much.
Thank you.
Thank you very much. Thank you.
Congratulations,
Dr.
Dipain, and best wishes for the program. Welcome,
you,
Dr. Hamid Raja.
Thank you. Thank you very much. Thank you.
Participants, just a note for your reference. You please keep your mic off at the time of deliberations, and whenever you feel any queries, you please raise your hands so that the queries can be taken, and accordingly those queries will be addressed. But please keep your mic off at the time of presentations.
Dr. Dipayan, may I start?
Yes. Yeah, please, sir. Please, sir. Please, sir.
Okay.
Please, sir.
Okay, so thank you very much. And hello, everyone. Welcome to the course as the resilient control of the cyber physical systems. So as I introduced my name before, so my first name is Hamid Reza. The family name is Karimi. So I'm coming from the Department of Mechanical Engineering, Politecnico di Milano. So as already announced the schedule of the course, so today we have the two parts. The first part is about introduction to the network, to the CPS, and also some challenging topic we had in this context. So after that, I'm also trying to give another lecture about some control design based on for instance, the slide remote control. So let's look at the introduction part. So if you look at the introduction to the CPS, so
sir, sorry to interrupt you, sir. Your screen is not visible, sir.
It's not visible.
Yeah.
Okay. Is it okay now? Can you see my screen?
No, sir, it is not visible at my end.
Okay.
Participants, can you please confirm whether the screen is visible to your end or not?
Okay, I can share it again.
Yeah,
so
yes, sir, yes, sir, yes, sir.
So can you see my screen now? Or?
Not yet, sir.
No, it is visible, Dr. Dipayan.
Okay,
the screen is
maybe it is not visible at my end, sir.
It is visible, sir.
Okay,
Okay.
Sir, please, sir.
Okay, thank you. Okay, so the first part, I'm going to talk about the introduction to the topic of the CPS. And in this context, I'm looking at some challenging aspect in this area. So if we talk about the network control system or the topic of NCS, so we know that this system, it has a component including the physical plant, sensor integration, control design, actuator device, and also the communication networks. In this case, the systems are connected through the shared communication network.
Dear sir, you are unmuted, not unmuted. Your voice is not coming.
Okay, oh, sorry. So I think let me ask you again. So is my screen visible and can you hear my voice?
Yes, now it is visible.
Okay. Thank you. Okay, so I talk about the NCS as a starting point. So the NCS consists of a distributed plant and also sensor actuator integration. And of course, the task of the control, it consists of some sort of a sampling physical signals. We have a computational control design and actually implementing the signal through the actuator as a control input. So if you look at this structure of a distributed plan, so we can get some benefits as a remote access, remote operation, remote control, and also the context of the distribution of the system, and also the perhaps the low installation cost and also maintenance cost. Okay, so moving to the decentralized control in the context of the NCS is one of the emerging topic. But what could be some drawbacks in the NCS? So there could be some challenges is coming from the networks, including the time delay, the limited bandwidths, and also the sending the data. And of course, we should expect some packet loss, the disorder, and so on. So you can see that the NCS potentially it consists of some challenges, and the main research in this context is to mitigate these kind of the challenges through the different control design or the scenarios. So beside of the NCS, we have a topic of the CPS as a cyber physical systems. So this is a topic we're basically focusing in this course. So the first thing that the CPS potentially can become the intelligence system. So basically by adding some software networks and also some adding to the cloud, it means that the CPS can communicate through the cloud. Now we have a cloud-based design, and also we have issues about the series of industrial and information technology can be integrated in this system. So the system of the CPS, so they also call it as a basic integration of the physical and also the networks. And we have the issues about the computation, communication, and again, the control. So very similar to the context of the NCS, the network control system. Again, we have a basically the sensor positions, sensor selection, and also we need to look at basically the physical system itself. So the network the network also exists, and also we have issues about the cyber systems. So if you look at the CPS, so we can first of all about the system awareness, and also looking at the data sharing and also real-time analysis, and this kind of information so should be sent to some sort of the decision making for some the task of the system operation. So how the knowledge can be produced and how the knowledge can be circulated basically for the better execution or the operation of the system. Of course, the optimization is always the concern of the CPS. So now you can see that the circulation of the system operation for the CPS is based on the data, and this data, of course, should be transmitted through the networks and other physical aspects, including the sensor, actuator, and also the system itself is also exists. So now you can see that this kind of CPS potentially has given a lot of benefits from technology. At the same time, we should get a lot of concern in different aspects. So that's it. The topic of the CPS should be integrated with some other keywords, for instance, about the resiliency, about the security. So these are some issues that become very important from application side. So based on these scenarios, so we need to a little bit get a better understanding about basically the effect of each item, specifically about the data transmission. And I'm going to talk a little bit more about this topic in the introduction part. So now you can imagine that the many industrial aspects we can expect for the CPS, for instance, about some wastewater treatment plant. And this kind of the treatment plant, I'm sure that in India has also a lot of interest from application side. And this system, if you want, I can explain. So you can see that the system has different levels. So from the basically from the operation level or the human level and come to the system level. And this system is quite distributed. You can see that it's a distributed system. There is a lot of subsystems. And how the knowledge of the expert, I'm talking about the owner of this plant, so could be sent some set point with the different subsystems. This is a very challenging topic. We have a network integration, then we need to look at the cybersecurity, resilience, As you can see that this could be one example, and this example basically very important in different location and specifically for India. So another coming to the technology in the internet-based teleoperation. Again, we have a sort of the teleoperator as a master manipulator and also some slave manipulator. So this kind of the teleoperation, you can see that it now become very emerging topic in the manufacturing and also in the health. In Italy, we have the big European project about the teleoperation for the surgery for the in the hospital. So you can see that in this context, because the data transmitted through the to this communication channel, and then you need to look at again the topic of the CPS and other basically the treats coming to the CPS, and then to see that how the signal could be healthy sent from the master to the slave part. So we can imagine that in all of these industrial applications, so the security and also the resilience of the system is of a high importance. So for this aspect, so for the NCS or CPS, so as we discussed before, there are three components: the plant, network, and the control. So the plant means that we need to have the information. Information means the modeling. If you have the model of the plant, then you can do the good analysis, a constraint. So here the performance, the stability, and also all the issues should be managed in the design. And that's it. In this course, we are talking a lot about the different control scenarios. For instance, a sliding mode control to get not only the fast response and also the limited time. It means in a finite time. So you should get basically the response with a good robustness. So now you can see that in the topic of CPS NCA depends on your interest. If you want to touch to the modeling or touching to the network or the control, there is a lot of challenging topics. And of course, these are the matter of discussion papers. And in that time, they focus on the future trends in network real time and wireless network. And this was a very successful special issue. And then there was another special issue in the IEEE Control System magazine. And in this special issue, basically, again, in the same year, 2007, so the other important scholars, they put the topic of the complex network control system. And this is one of another opening the research line. So there could be other research become the hot topic. So again, the topic of the new topics has been added. So one of the new areas has been added is the resiliency about the cyber security, and that this becomes an important topic discussed in this course. For control systems in 1998 was introduced by. So now we can notice that distributed plant and also real-time control. It means that the integration of the physical process, the sensor actuators, and also controller through the communication networks. So this integration should be done in the real time. And this data transmission between the device, so this is one of the key aspects of the utilization of NCS. So how we can realize the resource sharing, coordinating, manipulation, and also saving the bandwidth. These are some topics we need to look at the data scheduling from the sensor, basically to the controller through the communication networks. So we have some typical NCS. So this is a model of a network control. So again, we have this kind of the plant. We have a controller. So we have the sensor and also coming to the networks and also sending it to the controller for computation. Again, the data should be sent back to the actuators. So this is a typical NCS and also at any position. And the network characteristics are making the important role in these scenarios. Okay, so if you want to make it as the filtering part, as an estimation, so the same the issues we have for estimation or the filter design. For instance, if you have a physical plant, and if you have some sort of the input as like a noise or some other information, so if you look at the two kind of the data, so this is your signal, for example, as your target signal, and the signal Y could be the measure signal, then you can see after filtering, so you can get the better estimation of this target signal, and then you will have the error signal. So in these scenarios, so we can see that this is filtering part, it works based on if you could have a better filter design, and then the error signal could converge rapidly to zeros. So this could be the traditional, but if you want to take it over the networks, again, the data from the sensor should be sent through the network. So now you can see that the network-based filtering diagram, it means that the measurements are sent over the communication networks. So again, here is very similar to traditional approach because we are analyzing the error signal, but here what is the additive part is the information of the network, and this brings some challenge basically to the estimation part. Okay, so the advantage of NCS respect to the point-to-point interconnected control systems, the first thing is increasing the system reconfigurability. It means the scalability can be enhanced. So you can enhance the resource utilization, the reliability. So you see that the reliability can be enhanced in the context of NCS, because if you send less data to the event-based control, then basically the system performance can be enhanced with the saving the bandwidth. So reduce the installation, the maintenance cost, because for the wire point-to-point control, you can imagine how much cost goes for the installation part. But for the NCS, you can reduce, you can minimize the installation and also maintenance cost. So supporting the distributed control and intelligent device, it means that you can move to a smart control. It means that a smart device, a smart sensor. It means that the distributed control not only enhance the system resiliency, also they can also bring the opportunity to use a smart device. So based on these advantages, so the NCS becomes a very hot topics. And then there's a lot of research you can imagine for NCS. So if you look at the networks, network system, network device, control system, so all of these, they bring some gaps for the research. So, for instance, if you look at the network control system through the network system, network device control systems, so we have a lot of issues about the stability and the performance. In the real-time processing, communication through the control applications, and also about the timing analysis, the modeling. We can expect many the issue is an infrequent sending the data to the networks. So but in the data networks, usability, so on the scalability and also on the so based on the basic the type of the basic network protocols, so this could be implemented for this part. So it means that shows that the sort of the prediction and also the measurements. It means that without using the physical device. But again, the data acquisition, communication ability, and intelligence, these are basically the important aspect of a sensor and actuator. At least these are some important aspects. So when it comes to the controller, how to handle the decentralized information as well as the centralized information. So there could be a huge discussion how to move on from the central management level. These are the human knowledge. You see that the important topic in the CPS or NCS is how to get integrated the human knowledge or the management knowledge or the operator knowledge based to the system operation. So this topic of the HMI, so nowadays in Industry 5.0, in Europe is one of the key topics. How to integrate, how to look at the interface between the human machine, another interesting topic. And now there is another keyword as a HMCI. Either you have a physical plant, you have a knowledge of the model, or if not, you have a data-driven model. So you need to look at this. So for instance, in the control system, you can look at the direct structure. It means that in the direct structure means that the controller is between basically first of all, the sensor actuators are at the same side of the plant, but only the data from the sensor to controller to actuator goes through the networks. So this is basically the sensor measurement control signal, and this is we call it a direct structure. The direct structure means that the sensor actuator and also plant, they have this orientation. So another is the hierarchical structure is a bit different. So in the context of NCS, it means that for these scenarios of the plant and also the sensor and actuator you can see here, so there is a sort of the remote system between the sensor data measurement basically through the networks to the main controller. So now based on this kind of the data packet sending from the sensor measurement and also to the main controller and to send to the actuators. So there is also the one unit as a remote controller. So this remote controller, this also will be added to this remote system to the system operation. So this could be another architecture-based component. So two components as a wheel set. So this is one of these components, and then you can see that for the train, so that there are two such as the wheel set. So this name is a bogie. So the name of this device, if you are familiar with the train dynamics, so the name is a bogie. So you can search it. So bogie. So the bogie is basically for the transportation, basically for the wheel set of the train. So because India now is investing a lot on the train and basically for the intelligent transportation. So I would like to mention that one of the difficulties for the improving the technology extension system is for connected to the car. So because of the complexity of this device, so there is one issues about how to control it, and that's the topic of the network control. So it's become as a modern railway. So if you want to look at this research about the diagnostic, about the monitoring, so I would like to mention that in Italy, so we are looking at the bogie control and also the how to control this device. So this is the pantograph. Pantograph is getting the electricity to the train. Okay, this is for the power. This is for the power. So now you can imagine that if you move on to the modern railway, so you have the electricity from pantograph to the train. Here you have some Ethernet networks and you have some sort of the control of this device. So how we can manage to do it, because all the train can be controlled from the control room, from the CCR. So now you need to look at how to look at the train to control and also monitoring the diagnostics, and how to look at the operation of a different component on this device. So if in India your interest is on the rail and also on the technology for the train, and specifically to look at the control or to look at the cyber security for the such application, so you are very welcome to contact me, because our laboratory is a very advanced laboratory to look at the very complex challenges we have in this area. And this was information for you, because I know that India are not investing a lot on the rail, and this could be one of the very challenging and important topics perhaps if you are interested, we can discuss in more details. So I personally teach this boogie from the modeling for the master students. But if you are interested, I can also give you some material about how to model this device and how to look at the stability of this device, because if the speed of the train, so one question for you is that if the speed of the train increase a lot, why the train is out of control? And this is one question, how we can look at the high speed train. High speed train, what are the limitations? So if you are interested, I can also explain in one of the tutorials for you. Okay, so now you can see that in the topic of the NCS, so we have a lot of challenge. One topic is the signal transmission delay. So another topic could be the delay in the communication due to the buffering and propagation. So delay are bad for controller. So from the sensors to the controller to the networks. So this could be the normal sampling. It means that we have some sample data, and these are the 3 samples from your measurement YK. And this sample data can be sent basically to the controller node. Okay, so this is a signal YK. So for example, here you have a signal YK. So this signal can be sent to the controller, but now you can see that the data you can get at the control node, so a little bit shifted. Now you can see that this signal can be sent to here, and also this can be, for example, come to this position. So this is some sort of delay. So TKSC is the time delay between the sensor to the controller. So when you send again this data after the computation, based on the delay from the control to the actuators, there is another delay, TKCA. Now you can see that this sample data so can be shifted to the right. And again, this is also another basically delay can be added. So now the data is this is your sample data at this position where is reached to the actuator. And then if you want to send the control signal, if you want to send this control signal, it could be like this. It means that the control signal can be updated at this time, and not only at the sampling time K-1H. And if we look at here is the K+1H. So now you can see that the data can be updated at this time, and also the data control can be updated at this time. So this is the normal sampling. But let's look at another sampling as a vacant sampling and the packet loss. So the packet loss can bring some difficulties if, again, based on your sample data, for as we discussed before, this could be the YK. So let's look at the first time delay. So this is TKSC. So now you can see that if the TKSC is relatively large, basically for the first sample data, because the delay is a time varying. So in these scenarios in the network, we have a time varying delay. So if this duration of the delay is relatively large, and then you can see that in this sampling from K-1H to KH, here there is no data, it's a 0 data, okay? But here you have a 2 data, one is the red and one is the green, and this means that some data has been lost, and this is a packet loss in this sampling time. But the system cannot send this red signal because the system can send only the green signal to that position, and now you have only 2 sample data. So what about the red sample data? So this data has been lost, and that's it. If you look at the control signal, for instance, here you have some vacant sampling, and if no information, if there is a 0 information, means that the control signal cannot be updated. And that's it, the same control signal from sampling K-2H. So in this sampling time, the signal is a constant and not update, and the signal can be updated only at this time. So this is a challenge. So this part is a challenge, and the first challenge is stability, because at this position, at this sampling, at this position, so stability is a big concern, because how to guarantee the performance and control stability of the system. There is no any guarantee, and that's it. In the case of the packet loss, important issues is about stability, and we need to prove that the system can be, for example, can be stabilized. Stability, okay. So stability is one of the challenging topics. Okay, so now you can imagine that the NCS challenge and the solution. So basically, we can't. Okay, so there is one question. So yes, please. Okay. Do you have any questions? Yes.
Yeah, sir, I had a doubt that in the previous explanation, when one data is getting into the arena of the another data, so on the next step in the actuator node, how it is reduced to only one data in that time frame?
Okay, so good. So at this sampling time, because this red signal is a sample data coming from this K-1H, but the system is ordering. The system can react to this to the green signal, because here you could expect some congestion of the data. And that's it. The system so basically can react to the information of the green signal, because the red signal is out of use, and that's it. For instance, if you look at the sensor data from controller, from the sensor to the controller, so the green signal arrives at this position, and the signal can react to this signal. So this signal, in fact, is some packet has been lost, and also that has been rejected by the signal, because you know that the network has a sort of the delay. So it means that at this sampling time, we should expect that we have a sort of the duration of the delay, and based on this delay, the system, the networks can send the data can be received at the controller point. So, and based on this time delay is already defined, because for example, the t at the sampling time tk is c, so it could be between the two is greater than eta 1 and is also less than eta 2, for example. So now you can see that you only know about this lower bound and upper bound. So this red signal, it might be is less than eta 1. And this is a very challenging topic, because now then you have a congestion. So then you have a two information, and that's it. We call this, there is a congestion information. And this is I didn't talk about this point. Updated at the which sampling time. The sampling time based on the maybe I at this moment I don't open the topic of stochastic control, because this signal, because this sampling time can arrive at any time. At any time, if you could accept some distribution profile for this sampling time, and this distribution profile could be some stochastic process. And that's, yes, with the packet loss, with the sort of this kind of the challenge, the system should sampling, and this kind of the question, it opened the discussion about the stochastic stability. But of course, if you are interested, I can provide you some additional proven. But in fact, the important for the delay, so is the lack of information about the delay itself. And that's it. The only information you can expect is about the lower bound, upper bound, and you can do it with some tests. For instance, in my laboratory, students can do some tests on the network side, and they can get a better estimation about the delay information. Of course, the delay has been progressed a lot, and all the discussion on the delay is only how to get the better knowledge, and this better knowledge means how to model it. But in fact, in the NCS research, so the delay also the connected to the data, the sending and receiving over the network. And the networks, it could filter some data in some sampling point like this. And then this kind of the missing the data depends on the duration of the delay. So this means that we need to look at some probabilistic basically feature of the sampling time or coming to the sort of the stochasticness. So these are some issues. Basically, you can find many state of the art in this area. But as I told you before, that the time delay in the network is one of the key issues, and because we are looking at the quality of control, this topic is exactly shows how is the quality. The quality means the performance. On the top of that is the stability. So that's it. Here the big challenge is how we can guarantee stability with such the challenging aspect in the message rejection of the packet loss. Okay, so any other question?
Okay, thank you, sir.
Thank you. Okay, so I think for the NCS challenge, as based on the good question you mentioned, you see that always stability is the first. It means that we need to basically to look at stability and also delay compensation. So these are the basic two important topics. Always come first, and the second after stability is coming to the performance enhancement. It means that how we can look at the bandwidth allocation scheduling. And for this topic, basically for this topic, I will talk about I will discuss about the event-based control, and this is a topic we have in this course. So network security, and I will give you one tutorial about the security for the connected cars, because in my research group, there are some PhD students. They work on the security or the cyber security for the autonomous cars. And I can show you some result about the network security for the cars. So again, you can see that another challenge is integration of component and distribution of intelligence. So these topics coming to the machine learning, AI, and how the machine learning can be integrated to NCS. So of course, one of the benefits of machine learning is for the monitoring, and that's it. In my research group, one of the group is the condition monitoring. So we are looking at the condition monitoring, basically the monitoring of the system operation from the sensor, actuator, or the whole system components for mechanical, for electrical. So now you can see that there is a huge amount of the challenge we have in NCS. Of course, we have solutions. So in this course, we want to give you some challenge, and of course, we want to provide you solution. But of course, we cannot expect that we can handle all the challenge, because the research and the teaching are integrated. So in this course, we are opening some important topics, some challenge, and we try to address some solution. Of course, it depends on your interest, depends on your research profile. So you could expect maybe some other challenge, and you need to look at other solution for your problem. And that's it. When we talk about the CPS, NCS, we need to look at application. So in the future, if you have some particular application in mind, so please let us know, and then we can discuss more specifically, because nowadays there are many applications you can imagine, and this is very important. This kind of the research, they can bring you to some practical technology aspect. And if you are working the robotics on the robot networks, or you work on the autonomous cars, or whatever you are focusing on your research profile, so we can discuss, because the research comes from application in these particular areas. So about the delay, so just for your information, that I did work many years on some sort of manufacturing. So manufacturing, of course, in India also there is some research universities or the companies very deeply focus on the cutting process. So the cutting process nowadays is doing on the network, because all the machines, they work on the sort of the network base. So for your information this is one example if you want to see how the delay is appeared in the cutting process. So here do you have a workpiece, and this workpiece there is a cutter. You see the cutter, they try to basically make a surface. So this cutter has some suspended mechanism in X and Y. This is a two dimension, and with the speed of the omega, it try to rotate, and then you try to basically control it by applying the particular input signal, and then you generate the surface. So what is the problem? The problem is that this system can be modeled as a spring and damper vibratory model. It means that this system is a two-dimension. So you have the two forces in the direction x, fx, fy, and these two forces, so they can be modeled, so based on the spring and mass and damping. So here you have based on acceleration, velocity, and also position in the x, position in the y axis. This should be y dot, so this should be y dot, and this acceleration. So mx is the inertia, cx is the damping, so the cs is a damping, and the kx is for a spring. You see that this is a spring for a stiffness. So now here you have a damping, so I can write it here. So you have a damping, and also you have a stiffness. So a stiffness, so basically is for the parameter f. So a stiffness, okay? Okay, so if you look at the two forces, fx and fy, and based on this mathematical model, then if you start to look at the surface can be generated. So here is the same problem, you see? So here you have two forces, here you have two forces, you can see. And this is exactly the same x and y, and this cutter starts to rotate. So at this position, if you look at this position, is the tip position of the cutter starts to touch the surface. Okay, so this area, so this area can be modeled like this. So like this point, it means that the cutter they touch the surface, but there is some oscillation, you see, and this oscillation means the quality. If you want to get a good quality for the good surface, so you need to have a much more soft, a smooth surface. And why the surface is not a good quality? Because of vibration. And that's it. The topic of the vibration is very important topics. And in this particular case, you need to know that how to mathematicize the delay. So I think one of you asked me about the delay. I want to tell you that in this particular application, so if you try to mathematicize the model, so about the chip thickness encountering the bitutes, it means that here you can see that there is some vibration at the touching point. So here you can write some mathematical function basically for the deviation of the delta x. It means that the delta x is xt minus t. And delta y is the y minus yt minus t. So now you can see that the delay or the parameter t depends to some parameter like the rotational speed and also the number of teeth. Okay, so how many teeth is on this cutter? And also you see the z is the number of the teeth of the cutter. And also the omega is the speed of the rotation, of the cutter. Okay, so now in the practical application, so the delay, for example, this delay you can see there is a model like this, and based on that, you can basically find the speed of the spindle. So this was the one example for you to see that in practical application, so you could expect a delay. So one source of the delay could be the network or could be some issues about the vibration. And this example was exactly presenting this point. So for this cutting process, if you want to start to make a model, so here is a dynamical cutting force. So this is a dynamical cutting force. It's a mechanical model. As I showed you before, you have a two force Fx, you have a force Fy. So, but the point is that you can develop, because the model is fully nonlinear, and then based on the vibration and the cutter, so you can get the two forces. You can develop some transfer function after some linearization in the linear form. You can obtain some transfer function with frequency. So usually, because the system is a two-dimension, because this system is a two-dimension, is a 2D, so you can get the four transfer function. You can see. So this four transfer function is appeared here. Okay, so you can also obtain some transfer function as a direct and cross transfer function. So these are some function you can obtain, but I'm not going to much detail, but just I want to show the main idea. But this transfer function, so here you can see that there is a sort of the delay is appeared as a parameter t, because my focus is about the t. So this the delay is appeared in the sampling time. So in the Laplace transform, you can get this exponential term. Okay, this exponential term is represent that this is your ideal transfer function, and this is the transfer function after the vibration effect. So if you look at this signal delta x, delta y as an error signal at this position, so you can obtain basically this kind of the information in the frequency. But okay, so this is about the appearance of the delay. So, but in this case, if the delay is appeared because this exponential term should be added to the model, then you need to add this exponential term for the delay. So now the delay is appeared in your transfer functions, and then what you need to do, you need to design the control and to compensate the delay. And so now the topic of the delay compensation is important. But in this application, so you know exactly the delay, because I showed you how to calculate it. And then the next step is to design the control. And this was one of the projects we did some years ago. And if you're interested to some sort of the application in this area, so you can contact me. So another project we did also is important for India, because India is a large country. One of the big challenges is production networks. So production networks is also something like the network control system is distributed, it's a large networks. But the point is that in this application, so if you look at the picture on the right, you have several autonomous working systems. They work in the autonomous way. But in the production networks, you get some set points. So this is set point as basically some orders. So they want to give it to the networks. And then the VIP is the work in progress. It means that the VIP shows the capacity. VIP is the capacity of the networks. Okay, so in the production networks, one item is the model of the network, is the autonomous system. You can see they are connected. So this autonomous system in India could build the production network for some goods. For example, they are producing some goods, or even they are producing the fruit, for example, or transportation of the fruit from south of India to the north of India. It means that you have a large production network. So there are a lot of autonomous working systems, and they are connected. But the point is that you get some order. If you get the order, the system should start to operate, and the system will look at some sort of the work in progress VIP as some sort of in the system. And finally, you can get the order flow out. It means that you need to get this order flow. But in the production networks, in this project we did some years ago, we look at these issues about the total number of the input orders is coming to each station or WI. This is a dynamical model of the orders to the system. A total number of the output orders, omega O, and also VI day in the capacity of each station, because they cannot react in real time. If some order arrives, it should be stored, and after a few days or a few weeks can be sent it out. So now, if you imagine that you work in the production network for the food in industry in India, so one question is that how is the model of the capacity of each station? How many about the delays appeared, and about the network of the production system, autonomous system. And what we did in this project, I did it with Germany. So this project was for the food industry in Germany. So now you can see that you can get understanding about the delays and also delay compensation. And this is the autonomous system, and perhaps depends on your interest, you can use it. Okay, so because of time, so I talk about this, but I want to switch to one topic. Basically, is very important. So as a basically just a moment.
Excuse me, sir. Can you share your slides?
Yes, sure. I want to start the second lecture because do you have any question about the first part? Or?
If you kindly share the slides, it will be great for us.
Oh, sure. I will send you all the material through the course coordinator.
Okay. Thank you, sir.
Okay, thank you. Okay, so the second part I want to discuss basically is about the design issues for control systems. So for this part, I would like to tell you a little bit more about the design issues for control. So one topic is about stability, and we discussed before. So today we noticed that we focus basically on the sense, on the actuator, on the system, and also on the sensor model. But here, based on your data acquisition sensor data, and also based on the reference signal, so perhaps you could think about the performance and also stability. So for the stability and also the performance, how is the system is capable to follow the reference signal? Because one topic is about the reference tracking or adaptive control. It means that how to reduce effect of the measurement noise. Where we have a noise, we have some uncertainty in the model. So all these topics you need to look at in the design. When you design the control, first is stability, the second is the performance. The performance, it reflects the noise issues, uncertainty in the modeling, the disturbance, or even the reference tracking. So now if you design the control, perhaps you think about the feedback control. The feedback control, it means to enhance the stability. At the same time, you can think about the feed-forward control. The feed-forward control also basically can be useful basically for the enhancement of the performance. So that's it. Here you have a two control signal, and these two control signal, basically one is the feed-forward control, another is the feedback control, and the total control become the US. Okay, so this control signal can be applied. Okay, so if you think that the system is ideal, if the system is ideal, you can expect that the model of the sensor and actuator is identity. Okay, so for this identical the sensor and actuators with this function 1, so you have this typical system, and this typical system, you have a noise in the sensor noise, you have a disturbance actuators, and also you have some issues about the error signal. You need to bring it to, for the convergence, this should approach the zeros. At the same time, you need to look at the effect of the noise and also the disturbance. So for this particular case, if you want to start to analyze, so there are several transfer functions you can obtain it. So this transfer function, the first is a signal XS, so you can basically calculate it from this function. And also you can obtain the control signal US basically. So from this function, and also the YS is contain the noise. Okay, so if you look at this model of this system in the Laplace domain, the frequency domain, you can see that the noise is appeared here, and also the disturbance DS is also appeared in your case. Okay, so now the important thing is that if you want to get a better control signal US, so your control signal should mitigate effect of the noise, effect of the disturbance, but the problem is that the noise is appeared in the information Y, and that's it, the amount of the noise, how to look at the noise compensation. So this is one of the challenging topics we have basically in the design issue. So, but the point is that for this system with the 3 inputs, because here we have a 3 inputs, we have a noise, we have a disturbance, and also we have a reference signal. There are 3 information as an input signal. And then the relation between the 3 information and also to the 3 outputs, one is the XS and also Y and also US. These are the 3 interested signal. So one interested signal is a state of the system XS, another is the measure signal YS, another is the input signal US. But the point is that here you will get the 9 transfer function, because in this system, in total you have a 9. So in total you will get the 9. So in total you have a 9 transfer function, okay? So now the question is that if you want to design control, because only you can define errors, and you need to pay attention that how to design it in such a way that reference signal should be appear in the YS. It means that you need to do the tracking. If you want to do the good tracking, the error signal should go to 0. At the same time, you need to mitigate an effect of the disturbance, effect of the noise. And then everything should be based on this 9 transfer functions. If you look at here that the function Sn is represent also effect of the noise. So you need to mitigate for example, Sn should go to become less. LS should increase. So in fact, you need to increase LS, for example, LS to 1. If you want to increase LS, at the same time, you can see that LS is multiplied by DS, and then this also increase the effect of DS. So now there is a trade-off. Okay, so if you want to design the control, there is a trade-off between LS, SNS, and SLS. At the same time, you need to find the suitable control in such a way that, to find the optimal solution for this trade-off. Because otherwise there is no solution. Then this is a challenging topic that if you want to improve something, then another thing is also destroy the performance. And this is a problem we have. Okay, so what should we do? We need to look at the 4 functions. One is the transfer function LS. It's try to bring the reference signal to the Y for the tracking. So you need to look at the 2 sensitive functions for the noise and also the disturbance sensitive function. And also there is another sensitive function gives the measure process response YS to the measurement noise NS. Okay, so now you need to pay attention to the 4 functions in the frequency domain. So, of course, there is some background about the conceptual background coming from the both. So, if you look at the both statement, because both he wrote his thesis in 1945, you see. So he published his first state-of-the-art about the network analysis and the feedback amplifier design. So Boyd in the 1945, he introduced the topic of this function. So this is the basic, the simple case to find the trade-off between the basic sensitive function and also how to manage the grid. So the both says that this function over the frequency should be zeros and that's it. So this should be the basically the one solution basically to satisfy the performance of the system for the sensitive function. But if this function becomes zeros, then you can see that this function is an Ln function. It always should be positive, and some range should be minus, and then this becomes zeros, okay? So if you want to see that when is positive and when is the negative, so it depends to the length of S. If the S is less than 1, or if the S is bigger than 1, here you will get the positive, and here you will get the negative, and then in total you will get the zeros, okay? So these scenarios, it works, and this basically, we call it, we need to find a trade-off. So to check the performance of the system, and this is exactly the task for the design. Okay, so but if you look at this problem from the root locus, so in the frequency, so so you can see that in the Nyquist plot, it says that the function S, sensitive function, it has for example in this area, so is bigger than 1, and this area is less than 1. And then because this should be the Nyquist function, basically for the function R and G. But because the S, as you know, that the S is this function, S inverse is this function. Okay, so for this function, and based on the plan and the controller, so the Nyquist, the outside is a norm of S is less than 1, and then the inside is bigger than 1. Okay, so in these scenarios, you need to find the optimal parameter R, and then to see that in which frequency you want to get the norm of S less than 1, or at which frequency you want to get norm of S bigger than 1. So this was some conceptual background about the sensitivity analysis, but because of time, so I want to go a bit faster. So you can see that here we have some sort of the waterbed effect. Waterbed effect, it says that the norm of S, the magnitude, so in this area, so and this area should be enhanced, and this area should be reduced, because here you have a peak in the S function. So this effect, if you want to improve it, so we have a waterbed effect. It's like a sensitive dirt. If you remove the dirt from one side, the dirt goes to another place. So how to find a trade-off? This is the task of the control design. And this means that we need to pay attention how to manage this function S. Okay, so regarding to the disturbance on the load, so we have this block diagram. So first of all, let's assume that there is no noise. And for the parameter ds, so you can basically find the relation between the measured signal and a state of the system, and also relation between the reference signal and also the disturbance based on these two functions, ls and sls. Okay, so the RS is a control signal, is appeared in the both function as I showed you before. So now the point is that if you want to minimize effect of the disturbance on the design, so we need to pay attention the robustness of the feedback control system. The disturbance can be evaluated so in this way. So because the system is linear, you can impose the superposition principle, and first of G is bigger than 1, okay? So if the RG increase is bigger than 1, then you can see that the function LS, because RG increase, if the RG increase, so now you can see that the LS is approached to 1, okay? LS the approach to the 1. And what does it mean? It means that the SS is moved to the zeros. It means that the SS is moved to the zeros. And then in these scenarios, so the effect of the DS over the YS can be reduced. And this is one thing what we need basically to satisfy. So if you look at some simulation result, assume that you have a plan GS is like this mathematical model. So this mathematical model is a mathematical model for one spring and mass and damping. So one system like this. So if you look at the system like this, for example, this is a mass, a spring, and also the damping. If you look at the mathematical model for the motion of this, so this is the mass M. So now you can see that if you look at the position X for this system, so this can be modeled like this. So the model of this is a mass M, and this is a stiffness K, and also the damping C, okay? So for this system, so you can write this a function GS. Okay, so let's assume that you want to look at a stability. So for the underdamped, also the signal, the one-dimensional system, it means that, this system is a one dimension. Assume that you design the control RS as a PD control. Assume that you design the control as a PD. Okay, the PD control is modeled as this. RS is the KP multiplied 1 plus TDS. This is a model of the PD control. Okay, so if you apply this control to the system and then try to look at LS and KP, now you can see that if the KP, the constant KP, so increase, then you can see that the LS also increase. But this also clear that if the KP increase, as I told you before, that the R increase. If the R increase, it means that the L is also increased. And then you can see that here you can get a better control. At the same time, this is also the phase plot. So now, if you look at the function SS as a sensitive function, it means that if the KP increase, so now you see that the S also decrease. Because this is exactly you can see from this plot. By increasing the KP, so S is also decreased. So this is basically the effect of the parameter KP. So in the for the sensitivity of the disturbance. But please pay attention that in these scenarios only we have the disturbance. But here later on we also need to add the other feature like the noise. Okay, so for this particular case, so now you can see that in the time space, if you increase the KP, then you can see that the signal, the overshoot is also decreased and the signal becomes much smooth. So here you can see that here by increasing the KP, so here there are some mathematical model. Assume that the disturbance you apply is a step function. There is no noise and also no reference signal. So if you look at the steady state error, then you can see that the error signal after some computation. So if you write it down, so the error signal becomes like this. Okay, if the KP increase, so then the error signal it goes to zeros, and this is exactly you can see that by increasing the KP, so the signal plans. So one curve phase because if you look at the root Lucas, reason is that here you have an NNP zeros because of this +1, and this +1 is the NNP 0. Okay, so if you want to design the feed-forward control, you need to pay attention that the GS should be MP. The GS should be MP because all the zeros should be on the left. If the system is NNP, This doesn't exist. Okay. So now the most of the research you are doing so is mainly for the NP. But please pay attention that in many examples, like again, if you write the Laplace formulation between the x and y, and respect to the noise and the reference signal, you will get this mathematical model. So here you have the function Ls, you have a sensitive function Ss. So now the question is that if you want to satisfy the tracking, so Ls should increase. And if you increase Ls, again, you can see that the effect of the noise amplify the measurement noise, okay? So that's it. If you increase basically the control gains, because if the LS increase, then you can see that the effect of the noise also increase on the so that's it. So the system on the response is highly affected by the noise, and this is one challenge. So you cannot increase the control gains because you get the effect of the noise. Okay, so in this case, you can see that for the same example, for the same one degree of freedom system like this, if you apply the PD control, again, you start to increase the KP. So by increasing KP, then you can see that the LS increase, okay? LS increase, at the same time, SS decrease. But what is the problem? The problem maybe you can notice that at this position, if the KP increase, the SN also increase, okay? The SN is also, this is a problem because if you look at here, then you can see that if the KP increase in the high frequency or the KP, also the amplitude of the both plot in magnitude increase. So what does it mean? It means that by increasing the noise, by increasing the KP, so in the high frequency, the noise becomes more dominant, and that's it. They can, your result is highly affected by the noise. So this is one issue that we need to be very careful about the control strategy, about the parameter of the control, because all highly affecting on the response. Okay, so at the same time, for this case, because of the PD regulator, as I showed you before, so this time I selected the noise like the step signal like this, NO step T. So for this case, if you look at the steady state errors, so then you can see that by increasing the KP, so the error, it moves to NO. It means that by increasing the KP, so you can control R increase. If the control or the R or the KP increase, you see that if the KP increase, then you can see that the control signal, you see there is some spikes is also increased, and this brings some saturation. Okay, so now the point is that the noise, one of the issues we have, and control design issues should be fully basically to be carefully designed, specifically the type of the control. And because in this scenario, I show you that by increasing the parameter of KP, so even you could expect some saturation effects in your design. Okay, so I think we can stop at this slide because we can have a break. If you don't have any question, do you have any question? Or?
Sir, I have a doubt that when we are considering the two systems separately, like the measurement noise and the disturbances, so we are using the PD controller in that. So in the two different cases, we are getting two different characteristics of LS as we change the KP.
Yes, exactly. I think about your question, yes, you are right. Because here we have three players. So two players are the bad players, noise and the disturbance. The third player is the reference signal. So here, if you want to look at the control design, you need to look at the noise transfer function because this also it also moves to one, and that's it. The noise has a direct effect on the state and also they bring some issues even for the control. You see that here, I show you that by increasing the RS, so here you should expect this, and then you need to move to the PI control, and that's it. We need to look at the PI, PD, or integration to the PID control, and then you need to play with the more parameters. So with one parameter and also two players, or the three parameter or two parameters. So here I talk about KP. So if you change it, for example, to the PID control, if you move it to the PID control, then you have a KP, KI, and KD. Or even you can look at the PI control, then you have only the KI. So now the question is that the selection of the regulator RS is very competitive because it's a directly could schedule. So we can have a short break. So I think let's look at the schedule. So yes.
You can have your tea or water, whatever. Although it is not here in the department, so you can. Good evening, sir, and welcome back.
Okay, thank you.
Dipan this side, sir. Sir, I have sent you a mail. So whenever you get time, sir, please.
Okay, thank you.
That was regarding the feedback form only, sir. On final day, we required it, sir.
Okay, thank you. Okay, then if there are any questions, please let me know. If not, we can continue. So I try to cover this part and then to go to the another control strategy as a control, the slightly more control. But we discussed about the design issues. We noticed that we have three players. We have a noise, the disturbance, and also a reference signal, LS. Noise is also effect is also increased by the controller. So it means that the noise is directly appeared in your measure signal. So for this particular case, so the feed-forward control has no such a robustness respect to the noise, and then you need to look at the robustness to the feedback part. But the sensor? This is the topic is about the sensors. Okay, in the sensor, one parameter is about the delay. Okay, so assume that this is your physical plant. This is your controller. The control is a P control as a P regulator, as a control P. So the function Ts is appeared as exponential for e power of minus tau s. It means that you have such a delay as a parameter tau, and if you give the sensor the state xt, and here you will get basically here you have xt, and here you will get basically the x, so size x, and here you will get the x t minus tau, okay, x t minus tau. Okay, so now the delay is appeared in your output. Okay, so the function is the e power of minus tau s. It comes to the linear analysis, we need to approximate it. And what approximation for e power of minus tau s? Approximation is e minus tau s. So when you approximate this function by the linear form, then you can see that the delays appear. But this parameter, it brings a lot of difficulties, because this gives you the exactly the zeros. If we look at here, this gives you the 1 zeros at the s or 1 over tau, and I can explain you later on. But let's continue. So if you look at the function ls, if you look at the function that you loop gain L, so based on RG, TRG, then you can calculate it from this. What's the problem? The problem is that if the damping decrease, the phase margin become unstable. So this is exactly the problem why the delay is a challenging topic. So now you can notice that by having a small delay, so the system stability become questionable. Okay, this is a simulation result. Then you can see that for the same system, if you have a P regulator as a P control, so if you increase Kp for a small delay, for this delay 0.025, so if you increase the delay, the system becomes oscillated, and this is a potentially unstable case. So as a summary, in the summary, we talk about the two functions as a sensitive function SS, and also the complementary function LS. So the summation is 1, and it means that if the L increase, S should decrease, and that's it. So we need to look at the load disturbance attenuation effect. It means that how the SLS, so it can be attenuated. You need to look at the effect of the measurement noise can be handled to S and S, and the function also should be controlled. So now the question for you is that if you want to do the tracking, if you want to only reduce the noise effect, or if you want to only reduce the disturbance effect, so what kind of control with which parameter of the KP, KI, KD. And this is a traditional control basically we have for the physical plant. Okay, so we notice that the delay is an important part, especially the sensor delay. And then you need to pay attention that how to look at it, the function as test to basically improve the performance. So, but another important topic we have in control is the combination of the feedback and also the feed-forward control. So, but usually in all the control textbooks, they focus on the feedback control. But if in the future, if you do some project specifically for some project related to the oil company or the oil and gas business, so most of the industrial plant they have in the oil company is based on the feed-forward control. So now you can see that the feed-forward control is also important from application, from industry. And that's it. It's good to know how to combine the feedback and the feed-forward control. Okay, so I think I can skip this part. I can provide you this example, but because of time, I'm going to the control strategies. So in the control strategies now we have a feedback, we have a feed-forward, and we have a feedback and also the feed-forward control. Okay, so I show you some scenarios how we can reach the combination of the feedback and the feed-forward control. Assume that you have this system. So this system is a 1 degree of freedom model, is a single degree of the vibrating system. This is a mass, this is a damping, this is a stiffness, and this is a force. This is basically the control force. So if you look at the hypothesis, the system is stable, and we are looking at the underdamped single degree of freedom vibratory system. So underdamped means that the damping factor, the T psi, this should be less than 1, okay? Something like this. And also the objective is the fitting in the mechanical system with the force Fc. We need to design the force Fc such that this mass, the reference to follow the reference signal Zref. Okay, so we want to see that how this mass position, the center of gravity of mass, how this parameter Z, so they can follow for example, the reference signal Zref. Okay, so this is basically our target. So you can write this mathematical model, and this mathematical model based on the mass, damping, and also a stiffness. There are two forces, F and Fc. So the force Fc, as I said before, is a control force you need to design. So there is another force as a force F. So this force F you can see here. So it's composed of Fp and also Fr. These are some external force. Okay, some external force or the resistance force so can be also added together as a one F we represented here. So the question here is about the Fc, because if you want to design the control, you can design either the feedback control, feed-forward control, or the feedback plus the feed-forward control. Then I want to show you that different design. So one design is like this. So this is your mechanical system. So I to show you before, this is a function model of GS. So you need to design the control. Assume that you design the PD control, okay, the partial derivative control. And the partial derivative control, so if you want to see the formulation between the error signal and also FCFB, so this formulation is valid. FCFB is a KP multiply ZR minus Z plus KD multiply this. Why? Because the force, because of the PD, you have here, you have a KP, you have a KP multiply E, Okay, I think I need to change my mouse. I think my mouse is not working properly. So here should be KP multiply E plus KD multiply E dot. So okay, KP multiply this is a E dot, and this is also the E. Okay. Okay, so for this case, if you look at this mathematical model and if you put it together, all the terms, so you will reach to this formulation. So FC, so is equal FP, FT plus KP multiply ZR plus KDZ dot R plus this term. Okay, so this term is the contribution from the reference signal because here you have a reference signal ZR. So this term, this remains, but this system remains because this is some constant term. But this term depends on the dynamic of the Z and position velocity. So you can bring it this to the left. And if you bring it to the left, so then you will get this mathematical model, okay? So in this mathematical model, so here you have basically the change of the damping, C plus KD, and here you have a K plus KP. So this is a very important. So basically when you design the PD control, so you are changing the damping and also you are changing the stiffness. And that's it. You need to pay attention that how much you need to change KP and how much you need to change KD because you are modifying both parameters. So when you design the feed forward control, I told you before that the feed forward control, so this should be the inverse dynamics. So this should be the inverse dynamics. So it means that even if you have here the G, so this should be the G inverse. This should be the G inverse. So G inverse, but I cannot write it properly, but okay. So, but anyway, so the inverse dynamics, so can be written like this. So but the point is that here there are three parameters, M, C, K, and also in the inverse dynamics, you need to change another parameter as the M hat, C hat, and K hat. Because you cannot exactly write the same model because this is your exact model, MCK. But when you want to write the inverse dynamics in the time space, you need to choose another parameter, M hat, C hat, and K hat. So this is the question because this parameter should be estimated. But if you don't have the exact parameter, then you should put some estimated values, okay? So, but if you choose this mathematical model for the inverse dynamics, so then here you can calculate the FCFF. FCFF can be calculated, so from this mathematical model, and so you can write it like this, okay? So what happened here that, so here you just follow the same shape of the system dynamics, but with another parameter for the mass, another parameter for stiffness, another parameter for the damping. And this could be your inverse dynamical model. And then you can combine this inverse dynamics with the mechanical system. And here you have also additional force F. Okay, and this force F, you remember that this is F is FT plus FR. And here the FD is coming from the basically from the inverse dynamical model, and then if you add it together, then I will show you in the next slide how to combine it. So it means that for your system, for the first system dynamics you have, so here you need to substitute FCFF as the feed-forward control. So basically from previous slide. So this is your FCFF. You can put it here, and then this kind of the disturbance. So this one is also goes with the disturbance here you have. So here, okay, with this disturbance FD, so this can be removed, and then you can write this this mathematical model. So in this mathematical model, so So in this mathematical model, you can see that there is some changes basically in the change of the mass, in the change of the damping, and also in the change of the stiffness. And basically, there could be some mismatching between the parameters. So I try to change my mouse just a moment. So basically. Okay. Okay, so now you can see that by adding the two different masses here, so the M hat and C hat and K hat, so basically we got some mismatching between the real mass and also the mass we have used it basically in the model like this. Okay, so now if the M hat is equal M, C hat is equal C, K hat is equal K, it means that you have a perfect matching. But in reality, you don't have a perfect matching, and that's it. You need to accept some uncertainty or some change of the changes in the parameters. So the feed-forward control does not modify the system parameter and does not influence the stability, and only the feed-forward control can affect on the performance, and that's it. So one question in all of the design is how to choose the parameter and also what are the effect of this parameter over the overall the performance. So this slide shows that the combination of the inverse dynamics, the feed-forward, and also the feedback control, and this is a mechanical system. And then you can see that by adding the feed-forward control, you can enhance the performance analysis. So basically, these are the mathematical model. They are representing basically all of the equation. So if you want to do like this, so from the writing a mathematical model, you need to write, for example, to these scenarios. But here you need to pay attention that here we have used the PD control, but you can use different control, like a sliding mode control or any other control, and then to see what is the result. And this is the question usually when I'm teaching this material to students are free to choose different control. So, but of course, we can start from the PD first, and then as a baseline, as a classical control, and then to move on to the other control. Okay, so the very important conclusion is this: if you combine the feedback and the feed-forward control, please pay attention that feedback control, they try to change a stiffness and change the damping. It means that you can enhance stability. On the right side, if you use the feed-forward control, then you can add additional care for the better tracking, for the better performance of the system. It means you have a sort of some mismatching between the different parameters. So it means that the combination of the feedback and the feed-forward generally allows to obtain the best system performance, and that's it. If you go to some industry, I always say the oil company because I did many projects with the oil companies, and I can tell you that all of the oil companies, they only mainly interested to the feed-forward control because it's very simple. At the same time, they can also get a good performance, but what about stability? Because in that business, stability is always guaranteed and there is not so much concern. But okay, so this could be one scenario I had to try to explain, but there are some examples like the robotics. So in the robotics, if you start to mathematicize this dynamic of the robot, so to do some task, for example, to do some sort of the following some particular position or the angles or particular velocity or particular acceleration. So it means that for this system, for example, if you look at this rotation of this pulley with this kind of a spring and mass, and it means that if you look at the particular rotation of this pulley, so you need to pay attention how to design the control F, for instance. But if you want to satisfy for example, the tracking, you need to pay attention that if you are using the PD control or other type of control based on what I presented now. So at the same time, there could be some loading or the disturbance over the plant, and that's it. So we need to pay attention that how to basically to look at the effect of this kind of a disturbance. Okay, so it means that for this model, so if you start to mathematicize, if you want to have a rotation tau for the position tau, and based on this control signal in C, for example, if you are doing the feed-forward control, as I told you before, that for this dynamical model for the rotation of the pulley, so with this inertia, damping, and stiffness, so you can obtain this feed-forward control with the J hat and also as the C hat and K hat. But the shape is the same shape. You see the same mathematical model, but only change of some other parameters in this model. Okay, so if you start to find a transfer function, so you can basically apply the feed-forward control to the system like this. It means your reference theta to the final theta, and then if there is no external force, so then you can basically get this mathematical model. If you have a perfect matching, what does it mean? If the J hat is J, C hat is C, and K hat is K, for the perfect matching, you can get the perfect tracking. But of course, if you don't have the perfect matching, you cannot achieve the perfect tracking. So if you want to design the control, the feedback control, you can use the PD control, okay? If you design the PD control like this, then you can obtain the same function LS like this. So what happened here, that here you can see that in this function, so that you can get the effect of the KP and KB. So basically in your stiffness and also in the damping, and it means that stability can be improved. And then if you combine it with the feed-forward control, you can also enhance the performance, and that's it. So the combination of the feed-forward and the feedback control, so basically if you follow this mathematical model, is very simple, but if you start to write it down, so for this mathematical model, there are two forces, the feedback and also the feed-forward control. So basically, so you can obtain it from these two expressions, and then you can close the loop. Okay, so this strategy is the feedback plus feed-forward control, and in many applications gives a lot of benefits. So again, I can repeat it again. So if you are doing in the Laplace domain, so here KP, the PD control is this. This is your plan, and this should be the inverse of the plan. But please pay attention that not exactly the same G, it is a G hat S. Okay, so if you start again to write down the expression in the Laplace domain, so you can write the theta S relation to force and also the feedback and feed-forward the forces, and then you can write it down the expression between the theta and also the reference signal, so based on this formulation. Again, if you have a perfect matching, the theta is exactly theta R, but we need to pay attention that we never reach to the perfect matching because we don't use exactly the same exact parameter of the plan. But from the mathematical aspect, this is the analysis. Stability can be enhanced based on the control feedback, and also performance can be improved based on the feed-forward control. For instance, this could be your the reference signal and also velocity and acceleration, and then you can basically, if you have the feed-forward control with the perfect matching, J hat is J, C hat is C, K hat K, you can see that you have a very nice tracking to one. It means that your performance is perfect because you have a perfect matching. But if you have a feedback PD control only, if you have only PD control, then you can see that for this reference, the response is a blue one. There is some drift. You can see the reason is that the PD control cannot guarantee the perfect tracking. Only stability can be improved. But now you have some offset in the tracking, and if you combine the feedback and the feed forward, so for the perfect matching, then you can see the very nice result. How we can achieve this good result? Because the feed forward, they can try to enhance the tracking, and the feedback can enhance the stability. And this is the main idea behind of this motion control. Okay, so if you have an underestimated stiffness, for instance, if the K hat is a half of the K, then you can see that you never reach to the target, and you have some drift in the response because you have an underestimated stiffness. And then if you have for this underestimated stiffness, if you apply the feed forward and the feed back, again you can get a better result. You can see. But if you have a better estimation, better result. So this means the knowledge. If you have a good knowledge of the system, you can get a better design. But if you have a less knowledge, you mean you are always is the underestimated case, and that's it. The performance is never reached to the ideal case. Okay, so these are the result of the PID control. For instance, for this particular case, these are the response and also the response of the feedback and the feed-forward control. You see that the green line, so the combination of the feedback and the feed-forward gives a good result. So basically compared to only the feedback or the PID, and this means that we can get a better result if we move on to the combination of the feedback and the feed-forward control. So in the case of basically the response, if you have a disturbance on the load, assume that you have a disturbance at the time 2 seconds, and then you can see that this disturbance can be compensated, you see. So they basically based on this design, and this means that the system has a good robustness, basically based on this strategy. Okay, so this is also the measurement noise. If you have a measurement noise, the measurement noise with this kind of the variance, so you can see that the response, the blue one is like this. It means that we have this kind of the measured data. This is it, and also this is our the blue one is our response. Always we get some drifts because of the measurement noise, and we cannot reach to the perfect tracking, and this is also the effect of the noise. So basically can be appeared. So the measurement, you can see the green signal because of this noise, you can see. So at the time 2 seconds, you have some peak, some jumping, and then this can be vanish, and then but of course the response remains to some offset because the noise exists forever, you can see. But this is basically you can analyze the effect of the noise. So as a summary, the feedback and the feed-forward control could give some advantages. So compared to each of them as a separately, because you can improve the stability, you can also improve the performance. But this is the design as a sequential design. It means that you can first design the feedback control, and then after design the feedback control, you can come to design the feed-forward control to get your desired response. So this means that only the important thing in the feed-forward control is the good knowledge of the system, because you need to have a good matching of the performance. Okay, so based on this discussion, we can a little bit talk about the resilience. So for this system, because the resilient system, control system, so basically in different applications like a power electric, for water-based system, oil, telecommunication, you can see that the ability to the network control system has provided a mixed blessing in the ability to interlock the system of systems. So the system of systems. Okay, do you have any questions?
Sir, depend the sites. Just I have a very small query, sir, related to the feed-forward control. So as we know, sir, and even you also have mentioned in your presentations that the feed-forward control requires the knowledge of the systems, explicit knowledge of the systems. So, getting the knowledge or informations of the disturbances which is coming to the plant So that is practically not possible. So in that situation, how can we proceed for the designs of the feed-forward control?
Thank you. This is a good question. Actually, when I'm talking about the knowledge, I'm just talking about the physical parameter knowledge for the system. I'm not talking about the disturbance or the noise, because the feed-forward is only needs information of for example, in this case, you need only get information of the jihad S. And in this case, only the important information is the physical parameter, like the mass, the stiffness, or damping. So now the other parameters or the functions or the disturbance noise is not part of the knowledge. Yes.
Okay, sir. Thank you. Thank you, sir.
Okay, you're welcome. Yes, okay, after this discussion about the complexity of the system in the control design, we need to look at either the feedback, feed-forward, the mix of the feedback and the feed-forward. And because from application is very important, because I'm not sure which kind of the business we want to do or correct in the future. Many industries, they need the feed-forward control knowledge. And that's it. We can come to another topic about the resilience. Resilience means that there is a system at any time, is a system of systems. So one keyword here is a system of SOS. So the topic of SOS is also the part of the CPS, and it means that basically we need to pay attention that how to basically we can look at the SOS in terms of the resilience. So because the system are connecting and also the even in different crossing industrial sectors, so the control system complexity basically exists from different aspects as we discussed today. So cybersecurity is also the part of the resilience, because the system potential is under threat, so from different sides. So you can see that in this graph, this is some basically some attack sophistication. So from, for example, 1985 to up to now, for instance. So you see that the sophistication of the attack increased. And that's it. The system potential get a lot of unknown attacks, and that's it. How the resilience or how to look at these cybersecurity attacks is very complex, and that's it. We need to include some more resilience in the control design. Okay, so if you get the targeting of the complexity in the control system to the more secure control system or the more resilience control system, you are trying to deal with the complexity of the cybersecurity attacks because it's growing very, very quickly. And this means that we need to pay attention to these aspects. So even another, today I talk about the human-machine interface, because as I told you that in Industry 5.0, so the human system complexity is the major task. How to model the human in interaction with the machine. So now you can see that the human interfaces are loaded with the data. So now you have a data, and the complexity of the gathering of the data for operator or dispatcher to interpret, how to interpret the data. So this interpretation, and this is the kind of the interaction between the human and also the machine based on interaction cognition. So today I discussed, I told you the HMCI, so the human machine cognition interface, HMCI. So HMCI is a very important topic in Industry 5.0. Not only human, not only machine, but also the cognition, perception, how will be added. So if you are interested, because in my group, we are working on autonomous driving. Autonomous driving, one aspect is the driver interaction to the machine, not only the physical driver, but also some perception, cognition. So this means that the sensor actuator, cognition, interaction with the machine, processing, all is a complexity we have. At the same time, so this complexity from this HMCI, you need to pay attention also from the cyber security, and that's it. Nowadays, if you talk about autonomous cars, cyber security is a very important topic, and I'm sure that in India, maybe there are many companies that are producing the cars, and for them it's also very important how to implement not intelligence, because intelligence autonomous driving is becomes practically feasible, because everyone can develop a lot of machine learning tools for the car driving. But what is important is the integration of the cyber security and also the machine learning for the or AI in the autonomous cars, because here we are talking about HMCI, human machine cognition interface, and this brings a lot of complexity we have in the resilience space. Okay, so there's some consideration arising from the complexity, unexpected condition adaptation. So I told you about the autonomous driving. At any time you have some unexpected conditions because environment changing, you have an uncertain environment. So distributed control to address the complex interdependency and the latencies, the composition of the interdependent control system elements to simple stabilizable agent. So because you know that this kind of the system is a system of systems, I told you that this is SOS. So for the case of SOS, you need to have some strategy to control the system at the different levels. So for example, in the context of SOS, so another topic becomes important is the multi-agent, okay? So when you talk about the multi-agent, so multi-agent, so for the multi-agent system, because the agents are collaborating, the agents are competing, then you need to control the different layer of the agent. At the different layer, you need to control, and that's it. How to stabilize? These are the some issues we have in the resiliency of the control. It means that in this context, you need to look at the hierarchical distribution of the agent. What is which task is the higher priority or the importance? So another topic is about the goal conflicts. You need to recognize the performance goals about in addition to stability, the security, efficiency, and other factors. You see that today we discussed about stability, performance. Now we need to talk about security, efficiency, and other factors. So overall, the criteria for the performance of the control system must be prioritized with the appropriate trade-off analysis. So now you see that the trade-off is appeared, because of resiliency, always you have a trade-off, and that's it, because you have another player. Another player is the attacks. And attack is the uncertain, is the unknown effect, and that's it. How to look at this trade-off is the important part. So you need to enhance the system awareness. It means that by looking at your data, and for the data sharing, and if the data want to be circulated, to be translated to the information, so you need to pay attention that this translation to information based on some condition of the process and control system component. And we need to be aware of the data, because in the data awareness, important is that you need to trust. You need to trust your data. And if the data is attacked, if the data, there's a malfunction in your data, if you don't trust the data, then the data cannot be transferred to information, because transformation or translation to information means the control, okay? So because what we are talking is about control. So this translation to information is control, because control is the information. And you can apply to the plan. And if you apply the wrong information based on the manipulated data, but this is a very strange or very important challenge. Another topic about HMCI, the human interaction. So as I told you, that the Industry 5.0 is exactly this topic about the human performance prediction, cyber awareness, and intelligent adversary. So now you see that in the resilience context, there is a lot of consideration we need to pay attention. So these are the some topic about the cost, the policy benefits. If you want to get some resilience metrics in the measurement, if you want to get some resistance in terms of the resilience design, you have the cyber control and the cognitive. You can get again some resilience design. So if you want to come to the consensus, so in terms of the recount for the CPS, you have a cyber, physical, and cognitive. Then you can get some state awareness as a recount for the CPS. And then if you want to come to the resilience, you have a resilience design. You need to get a resilience design, a state awareness, and the threat information. Then you can get some basically some by developing some accountable information, adaptive architecture, you can reach to the resilience. So now you see that measure, respond, recount, and resilience. There are 4 disciplinary and also in the context of the resilience of the CPS. Okay, so the you see that there are some statement. It says that next generation, the control system from reliable to resilience. So there is a very good definition. So basically, it says that the resilience is the capacity of the control system to maintain a state awareness and accept a level of operation normalcy in response to the disturbance, including the threats of an unexpected and malicious nature. So this is a very standard definition we have. So now the capacity of the control, the resilience control, and also how to keep the state awareness. This is basically the one of the important challenge, because resilience, you need to enhance the reliability, and because you need to look at your reliable information. Reliable information, as I told you before, is coming from this awareness, state awareness, because if the data want to be changed to the information, you need to look at the reliability. You need to trust, and that's it. Reliability to resilience is an important topic we have in the resilience control design. Okay, so there are some transformational threat resilience control system in the national challenge about the cascading failure, cybersecurity, and also there is some addressing challenges as an outcome. It means how to minimize the impact to infrastructure amnesia, intelligent architectures, diverse detect and the response protection at each level of the control system architectures, advanced control design. So basically, the asset degradation and the proactively control, cyber security and human factors. So now you can see that the challenges we already know about it. Some failures, some attacks, and the cybersecurity, and the outcome to enhancement. And this means that one of the important part is from the control, and we try to discuss it. But very also briefly, because reliability is one of the very important topic in the resilience control, because we are talking about the data translation. So, but one aspect today we talk about the centralized and also decentralized or the distributed. So you can see that if you have a reliable, centralized to resilience distributed control, so there are some comparison in the state of the art. So one issue is about the unexpected condition adaptation. It means the centralized monitoring and control interactions that are brittle to unexpected failures. So it means that if you talk about the reliable for centralized system, there should be some complexity, interdependency, and of interaction that cause emergent behaviors. So human interaction for the reliable centralized case, it means that you can look at the common complex human performance variables and variation. But when you talk about the resilience distributed control, even for the same human interaction, you can look at the prediction of the human performance. and also autonomy interdictions. So, or the fusion and the prioritization of the response based upon resilience priorities. So it means that for each category, for unexpected condition adaptation, human interaction, even the malicious actions, because in the reliable centralized, you have a lack of state awareness of the malicious actions. But if you come to the context of the resilient distributed control, so basically we have some active defense and also for deception, environment modification. So now you can see that adding the resiliency to the distributed control, you can get a better approach to deal with the active defense, respect to the malicious actions, better prediction of the human interaction, and even you can come to the some sort of intelligent behavior for the unexpected condition adaptation. So in total, we can get a lot of benefits. So of course, we can discuss more details. So for each part. So if no question, I need to switch to another topic. So because we have another topic we prepared for today. So this is about a sliding mode control. Okay, so I try to switch to the one of the control strategies as a SMC. So for a sliding mode control, today I would like to give you some introduction to SMC, some design and also applications. But of course, we have another session about SMC. I will discuss more, maybe also another lecture. But today, so let's start with the SMC. So about the introduction to a sliding mode control, basic concept, a type of variable, a structure control. So and some other issues about the type of system and design. So first of all, this is my recent book. So you see that the book is published end of 1st of May. So if you are interested, I can provide you more material from the book. So the book is about a sliding mode control of fractional order system. I'm not sure if you are working on the FOS fractional or not. But if you are interested to this kind of the systems, so you can contact me. And if you are interested to the book, because the book is published now, is not released, but in 1 month, I have access to all the book's content. But if you are interested, feel free to contact me. Okay, so now you see that the sliding mode control, it becomes a very important topic because of this robustness, and that's it. And also to look at the response in the efficiently in terms of the managing the response in the finite time. The finite time, robustness, these are some issues. We are interested to use it for some complex system, and that's it. We try to discuss about SMC, also for the CPS, and then to see that how we can get some enhancement. So the origin of the feedback control, we discussed about the control from ancient side coming to the classical control, coming to the advanced control. It means that the control is developing very fast. And nowadays, based on the topic of the course, you see that now the resilience control becomes a hot topic in the CPS. And that's it. We need to a little bit look at some new trends. Okay, so of course, from the state of the art, of course, maybe you are familiar that so the relay is one electrically operated switch. It means about switch control. Okay, so how to switch from the state 1 to state 2? This kind of the switching or the jumping. So the relays also would be one physical basic device. So it was useful in some circuit design, and therefore the relays was introduced or was integrated to the control system to perform some logical operation. And that's it, this kind of the variation in the structure by changing the modes of the system from 1 to 2, so or the vice versa. And this is the on-off control actions. So they bring some difficulty in control, because if you do any kind of switch, then you are jumping, and then there is some nonlinearity in the system response. And that's it. One of the problems appeared from the relay-based control is about the nonlinearity is appeared in the model because of the switch is appeared in the system model. Okay, so but of course there is a lot of development from late 50s, 60s, and also very famous person. He contributed a lot basically to this topic is basically the Professor Etkin, basically in his 1964. So he tried to introduce the variable structure control, is a VSC. Okay, so he introduced the VSC, variable structure control, and then later on is changed to SMC as a sliding mode control. But what he proposed, he also focused on the theory of the relay-based control, and based on this kind of the theory, and then he need to look at some variation in the system, and that's it, the VSC, and how to come into the SMC. So these are some keywords. So basically has been introduced. So originated from the work done by the Professor Etkin. Okay, so the basic concept is sliding mode control. So first of all, the basic terms, it says that we have some dynamical system like this, okay? So here we can see that for this equation, we have a control signal U, and we have a system state X. And then here you need to introduce some logic. And this logic is introducing by the function sigma X, okay? So this function sigma X, or we call it a switching surface, or a sliding surface. So is a sliding variable. So now the sigma is a sliding variable, and sigma x is 0 is a sliding manifold. So what does it mean, a variable, and what does it mean, a manifold? So the sigma x zeros is trying to give you one surface in the 2-dimension or even one line, but all the variables should approach to this manifold, and that's it. A sliding manifold can be introduced and should be selected, should be chosen, but this depends how many states you want to control, and that you need to add some dimension basically to the sigma x. So now the sigma x, depending to the control signal dimension m, it means that you want to control, for example, n variables, and therefore you can define the sigma xt based on this as a sliding variable with this dimension, vector dimension, and then you try to basically to design the control. So the concept of a sliding mode, so as I showed you before that, so it means that all the state trajectories, basically, so that based on that this d plus n minus m, it means that this sliding manifold is a subspace of the system state space having the dimension n minus 1. So it can be a sliding surface or be given by the intersection of the several surfaces. So this could be one single surface, or this could be either as an intersection of the several surfaces, and that's it. So this could be your sigma zeros, or this could be your sigma zeros, okay? So assume that for this kind of the sigma zeros, and then all the state trajectories, so they should converge basically to these sections. Okay, so now Okay, so if the state trajectories continuously cross the sliding manifold, since it's it's a vicinity of this state motion, always directed toward the manifold. So now the point is that when the state trajectories is hitting, so for example, this sliding manifold, and then they can push forward to move to the sigma zeros, and this means that the convergence can be guaranteed if we follow this concept of the sliding mode. Okay, so if you look at the design ingredients, so there are two elements. One is a sliding manifold. The second is a control law. It means that a sliding manifold is a sigma x. It means that how to choose the sigma zeros. And in this case, so this is one parameter to be designed. So the system in a sliding mode, basically, we try to look at how to asymptotical state can regulate it to zeros if they are basically coming to the sliding manifold. But the control law, it has to be chosen in order to enforce. This is very important. A sliding mode. It means that after a state is hitting, for example, or approaching to this sliding manifold, there should be some motion around of the surface. So it means that there are some sliding motion. And this means that the control law should be responsible to guide a state trajectory to this sliding manifold, and then to be remain after some saturation or some fluctuation around of this sliding surface. So a sliding mode needs to be enforced in a finite time. Okay, so reaching from this initial condition x0 to this point, so this should be done in a finite time, and that's it. One of the characteristic of the requirement for a sliding mode control or a sliding mode motion is the finite time behavior. This should be done. But please pay attention that in control we have two topics: finite time or the fixed time. Okay, so these are the two keywords. So basically, the time to time, so the fixed time. So you can see in many state of the art. So a sliding mode can be done in finite time, but what does it mean the fixed time? Fixed time, so it could be also one representative of the finite time, but the fixed time, it means that this should be designed by the user, for example, at the one specific time, so that the control should reach to the target. But this is different from the finite time, and that's it. If you want to design the fixed time control, so you need to pay attention that the time is already given, but the finite time is a short time. It means that the TF so should be less than infinity. Okay, but as long as this TF become less and less, the system become quicker and quicker. But the finite time is different from the fixed time, because in the fixed time you already have one force, one requirement to reach in this specific time, and that's it. A sliding mode just presenting the finite time. But if you want to bring it to the fixed time, so we need to look at how to modify the control strategy to satisfy this point, but this is another research topic. Just I tell you that another keyword might be you are interested to see what is the difference between the finite time and the fixed time. But SMC is only can prove the finite time, but SMC cannot guarantee the fixed time. But if you want to reach the fixed time, we need to modify your design, and that's it. These are the important topics. Okay. So the equivalent system and its properties. So the system in a sliding mode, it has two interesting properties. One, order reduction. This is very important because when you design the sliding mode control, the system in a sliding mode changes the order from n to n minus n. Why? Because you already m is coming from the dimension from the sigma x zeros, okay? because when you add some algebraic relation from the dimension, because sigma x, it belongs to Rn, okay? So now you can see that by designing this sliding surface or with the dimension m, you try to reduce the system order so to the n minus n, and this means that the computation also can be enhanced. So the invariance property is insensitive to the match uncertainties. It means that the uncertain terms affecting the system on the control channels. So that's it. This is one of the properties insensitive to this kind of the matching uncertainties, and this is also about the robustness. So the reduced order state equation describing the system in a sliding mode is called equivalent system. So basically this reduced order after designing the sliding surface, when you got the reduction in the order to n minus n, so this reduced order, we call it the equivalent system. So this kind its dynamics can be assigned by suitable design sliding manifold. So now important is this: how to design this sliding manifold sigma x, because all the challenge is related to sigma x. So one example. So we have this unstable second order system. So if you look at this system, you will see that this system is unstable. And then for this unstable system, we want to design the control input as a u minus 3x1 or u equal 2x1. Okay. So if you do like this, if you choose the control signal u as a 2x1 or minus a 3x1, so then you see that the control system has an unstable focus if the u is minus 3x1 and a saddle point if the u is 2x1. Okay, so if you look at the control signal u minus 3x1, and if you look at this equilibrium point, you see that they are diverging. They are diverging to infinite. Okay, and this means that you have this unstable focus. This is the unstable focus for u minus 3x1. And then for this, for the case of the u equal 2x1, then you have such a saddle position. You see that if you look at the state trajectories x1, x2, with the control signal u equal 2x1, you see that a state trajectory, they have such a behavior. So this behavior is the saddle point, and this behavior is unstable focus. And this is a two behavior you can see for the two different controls. Okay, so now you are choosing another manifold. If we choose a sliding manifold sigma as a C1 x1 plus C2 equals zeros, and C1 is positive, okay? So in this case, so the design control input as a combination of the two previous control laws. Okay, so now we are choosing the control signal like this. U is the K sigma x1 x1, but the K sigma x1 is minus 3 or equal to if the sigma x1 is a positive or if the sigma x1 is negative. So you remember that in previous slide, minus 3 was the u minus 3x1, right? And also this was the u1 and this was the u2 is a 2x1, okay? So we notice that this unstable system, this is a very good example. This unstable system with the two different control signal u1, u2, again is unstable. But if you bring it to the context of the sliding manifold, a sliding mode, but you choose such a switch because you are switching if the sigma x1 is positive or sigma x1 is negative, it's become minus 3 or 2. If you give a switch between the two control, and then you can see that this is a U2 and this is a U1, okay? Then you can see that the control signal brings you some advantage. The control law is a variable structure control law. It means that the control, there is some variation in the structure. The control system becomes the VSS, variable structure system, VSS. And this means that let's see what is the benefits. So based on this benefit, the combination of the two control laws ensures the conversion of the system state to origin. This is a very important. So as long as you are using this control signal as we discussed here, U is the KX1. So based on this control signal, if the sigma x1 is positive or sigma x1 is negative, then you can see that these can converge. So basically to the sliding surface, because here you are choosing you should choose the sigma like this. Okay, sigma is this formulation. So here you have a sigma is equal C1 x1 plus x2. Okay. So for this switching surface, so if you see that if the C1 is bigger than 1 or the C1 is less than 1, then here you have such a basically the 2 sigma is a sigma x2 plus C1 x1. So in this case, all the state trajectories so basically can converge basically this sliding surface. So from any initial point, so from this area or from this area, so basically the system can converge to this sliding manifold. So in this case, if the C1 is less than 1, a sliding mode is enforced. It means that we need to see that for the case of the C1 is less than 1, so then in this case, so we can reach basically to the sliding manifold, and this basically system can be stabilized. But for the sigma, for the C1 bigger than 1, there is no convergence. You see, there is a dashed line. Okay. So in this case, what we can notice that the parameter C1 should be less than 1, and then all the state trajectories can be approached to this manifold. Okay, so another example is we have the double integrator. So this is another example. So it means that for this example, if with this constraint over the control signal U is less than 1, so you can choose the sliding manifold, the sigma like this. Okay. Usually, you can choose the linear shape for the sigma, like a C1 x1 plus x2 equals 0, and the C1 is positive. So if sigma is equals 0 in a finite time, is a TR, the finite time as a reaching time, and sigma zeros, so a sliding mode, then the dynamics of the equivalent system in a sliding mode is of read disorder like this. Okay, so now this system says that if the sigma is equal 0, then the system has a reaching time as a finite time TR to the manifold sigma zeros. And then when it reaches to the manifold sigma zeros, so after T bigger than TR, the system has a sliding motion, a sliding mode. A sliding mode, it means that, for example, if this is your, for example, this is your sigma zeros, for example. So when the state trajectories is from the x at the time zeros. So when this arrives at this surface, and then it start to have some motion like this. So this time, so from here to here, it goes at the time TR, and after the TR, here after TR, there is some oscillation, and this oscillation, we call it a chattering or a sliding motion or a sliding mode. Okay, so for these dynamics, you can see that because the sigma is this, so if you want to write down so basically the equivalent system, because equivalent system, you need to add the sigma 0 to this state. So then you can see that the x.1 plus C1 x1 becomes zeros. Why? because you can see that from this equation, you have x dot 1 is equal x2, okay? X dot 1 is equal x2. So from here, x2 is minus, from here, x2 is equal minus c1 x1. And then if you bring it here, so this becomes is equal minus c1 x1, okay? And then if you bring this to the left, you can exactly get this equation. So this equation, you can obtain it. But what does it mean, this equation? This equation means that it is an equivalent system. And if you look at the state x1, you can get this formulation, okay? So this formulation says that because of this exponential, at the time tr, so the system can reach to the surface, and then the system can, there is a guarantee that the state can be vanished to zeros. But the point is that you need to choose C1, because by changing C1, the performance is totally changing. So now for this system, because for this double integrator, assume that you design the control input. So the control input is for sigma positive is -1, for sigma negative is 1. Of course, there is a discontinuity at the sigma zeros. Okay, so for this system, if you want to apply in the simulating, so you can choose like this. So like this saturation part. And then for this switch model, you can put in the simulating, and then you can basically to design the control. Okay, so if you start to close to look at the simulate of this closed loop scheme, so based on this kind of this saturation part, so we can see that the result can be obtained. So here for the small C1, if the C1 is a small, and this is for the large C1. So if the C1 is a small, the state trajectory is following the parabola arc, and then and reach the line sigma zeros, because this is the sigma zeros, and then basically they can reach. And then a sliding, they have a sliding toward the origin as a sliding mode. Then they can reach to the surface. So at any time that they can reach to the surface, and then to have some sliding motion to the surface. Of course, before they are following some parabola arc. There is a parabola arc. They are following such a shape, for example, something like this, and then they go to the origin. But if the C1 is large, for the case of the largest C1, so you can see the state trajectory follows sequence of the parabola arc closer and closer to the origin. So this is quite interesting that they follow different parabola. You see something like this, and then finally they can come closer to the origin, but no sliding mode is generated. So this means that if the C1 becomes bigger, you don't see any sliding motion, sliding or the chattering. They can become on the different parabola arc, and they are become closer to origin, and then they can converge to origin. So this is another behavior of the system. Okay, so now you can perturb the double integrator with an uncertain bounded term. So let's assume that in this, because this was your this double integrator, right? And this was your control. Now let's add this term. So now we want to add this additional term like this. We want to add the function dx1, x2, and t. And you remember that the sliding surface was this. Sigma is a C1 x1 plus x2. So this term is the uncertain bounded term. And if you add it, so here we can say that if sigma is zeros in a finite time tr, reaching time, and sigma zeros is we have it for bigger than the time bigger than tr, we have a sliding mode. Then the dynamics of the equivalent system sliding mode is this. So you see that these dynamics can be obtained. So from this mathematical model. So the uncertainty doesn't affect the system in a sliding mode. So this is very interesting. So maybe I think this could be a good exercise. So you see that even if you add such a disturbance, such a uncertain bounded term, so it never appeared in your equivalent system, because equivalent system is the same as before. So it's very interesting that you can see that x.1 is equal to x2, and as I showed you before, x2 is minus CA1 x1, and you can get this. So what does it mean? It means that this function d is it doesn't affect the system in a sliding mode, because of the structure of these dynamics. Okay, so what we can learn? One is about the VSS, about the variable structural control VSC and VSS. So making the system become the variable structure system can have a stabilizing effect. So it means that this switch in the system, such a variation in the structure, so then you can stabilize the system. A sliding mode enforcement depends on the choice of the control law. So it means that it's very important to this a sliding mode enforcement depends on the choice of the control law. It means how to choose the sigma x. And the system in a sliding mode is of a radius order. It means that when you design the system as equivalent system is a radius order, it means that the computation is decreased. The system dynamics in a sliding mode can be arbitrarily assigned. It means that you can choose the system dynamic in a sliding mode, depends on you, but we need to pay attention that how to select this sliding manifold, and this is an important task. The system in a sliding mode has a nice robust problem. So the system is robust, and this is one of the advantage basically we have from a sliding mode control. Okay, there are different type of the variable structure control laws. It means that one of the variation is that so as a relay control. So this is one variable as a structure VSC. So the relay control or the relay, so the control signal UIP depends on the sigma I, positive or the negative. So they should have a two levels control, UI plus, UI minus. So this is it with the dimension M, and then you have a sliding manifold sigma IX equals zeros. In total, you can find this sliding manifold sigma X. Okay, so the design phase consists in designing the sliding variable sigma x and the smooth function UI plus and UI1. It means that all the design, so whatever should be designed, we need to select the sigma x, and also we need to select this smooth function. So these are some design function or design variables. So you can choose it for the relay control. So a state feedback control with the switching gains. Okay, so now you have a control signal as a state feedback. U is a psi x multiplied xt. So this is a function psi. So is a matrix. You can see is the matrix n by n, and each term of this matrix is phi ij can be selected from this mathematics. It means that it depends on the sign of this function. So positive or negative, you have two levels, alpha ij and beta ij. So in this case, if you, for instance, the unit vector control, so if you choose the control signal u like this, so this is you know that this is equal to k multiply the sign is sigma x. So this control signal is also the unit vector. They call the unit vector control. So it also looks like this. You see that you can, for example, choose like this, and this means that the unit vector control is one example for the state feedback control with switching gains. But this is a general shape, and this could be another control, but you can choose like this. So the philosophy behind of the unit vector control is taken from the state feedback control with the switching gains. Okay, so there is some other control strategies, control based on the simplex of vectors. So that's it. This was one unit vector control, but you can think about the simplex of the vectors. In the multi-input case, the variable structure control philosophy can also be implemented by designing a set of n+1 control vectors forming a simplex in Rn. So the control system switches from one to another of this. So now you see that the idea behind of the simplex of the vectors is to give more flexibility by designing the more control vectors. You need to design a set of n+1 control vectors, and then the system can switch from one to another one. So now you have a more switch possibility. So if you look at this publication as a multi-input sliding mode control because of the answer nonlinear system, you see that so you can get a better idea that how this simplex of vectors can be realized. Okay, so there is some other discussion about the type of the system. So basically, the one is the canonical form. So in the canonical form, the assumption is that the system is nonlinear with respect to the state variables and linear with respect to the control variables. Okay, so it means the system should be affine in the control input. So it means that something like this. So this is a basically, we call it the system is affine in control input, nonlinear respect state variables, and also the linear respect to the control input. So this means that this assumption means basically I'm talking about this dynamics. The proof of the existence of a sliding mode and the design of the variable structure control are simplified if the considered nonlinear system is expressed in one of the following canonical form. So if the system can be represented in the canonical form, it means in the reduced form. It means a state vector xt can be split into the two vectors x1, x2. Okay, so if you put represent it like this, x.1 is a1 xt, no control, and x.2 has such a affine shape in respect to the control. So this model is a reduced form, and that's it. If you have such a model, it can be proved that the proof of the existence of a sliding mode is possible. We can prove it, and also we can design the sliding mode control. So this means that if you have any model system like this, the task is can be guaranteed that you can obtain you can stabilize it, and also you can find the control. So there is a contractibility form. So this is a reduced form, another is a contractibility form. The system is split into the M subsystems. Okay, so the M is the number of the control input. Okay, so each of them is the Bronowski canonical form. So let's assume like this. This is a contractibility form. Assume that a state, it has a dimension n. So we're basically, and each of the xi has a dimension ni, and the whole system has a dimension n. So now you see that the system should be split to the M subsystem. So now you have an M subsystem, and each subsystem has a dimension and I. The final system is x dot equal ax plus fx plus bx0. And the A is a diagonal AI. And now you have for each subsystem x dot I, you have this mathematical model with this matrix AI, this AI, this is a Fi, this is a Fi, and this is a function beyond. Okay, so if you could represent your system dynamics in such a shape, So this is a controllability form, and controllability form consists of the M subsystem. M is the number of the control input. Okay, so again, for if you represent like this, again, you can guarantee stability. Then you can also obtain a sliding manifold. So another is a decoupled input-output form. But this is for the SISO in the single input, single output case. Assume that you have a nonlinear system with the output Y as a CXU. This is your measured data for the SISO system. The system relative degree is the order of the time derivative of the Y in which the control U first explicitly appears. So if you have the MIMO case, it means the Y belongs to the RM. So if you for the given output Yi, the associated relative degree Ri is the order of the time derivative of the Yi in which at least one of the control variables Ui first explicitly appears. The system relative degree is this. It means that this is the relative decrease for the M input, because the order of the Y, the output is M. So then you have a several R1 to Rn, and each associated relative degree Ri is the order of the time derivative of the Yi in which at least in one control variable Ui is explicitly appear. Okay, so but maybe if you are, I forgot to introduce the relative degree, but relative degree, the definition is this. But if you work with a nonlinear system, so I think it means that you need to get the derivative from the Yi in order to get the control Ui out of this. So, but if you need more information, I can send you another textbook so to read more about this. But if you search on the internet, easily you can see that what is the time derivative. So time derivative means you need to take 1 or 2 or 3 to 4 times the derivative of the variable Yi in order that the Ui should be appeared explicitly. And this means that this is a relatively degree. But the system relatively degree, so for the whole system is R is equal R1 to Rn. If R is equal N, the total and relative degrees of the system is equal N, the system, this can be represented as a set of the decoupled differential equation like this. Now you can see that for this relative degree Ri, you can see for this derivative, Ui is appeared here. Okay, so now the question is that if you represent the system like this for this MIMO case or the size case, the system is represented in the decoupled input-output form, and then for this case again, you can design the sliding mode, and you can find a sliding surface, and you can stabilize it. So this is a canonical form. Okay, so another form is a normal form, but I think because of time, if you agree, I think we can stop at this form. And next time when I want to continue the topic of the sliding mode, so then I can basically continue this part and then to discuss. Because of the time, I think we can stop at this slide, and the rest we can discuss it next time. Do you have any question? Or?
Thank you, sir. Yeah. We can take 1 or 2 questions from the participants.
Yes. Okay, so I can provide you all this material present today to give it to the Dr. Dipayan, and then you can get access the material. But if you have any question, so you can come to the next session, or you can send me an email, or we can discuss it in the next meeting, so to discuss about it.
Surely, sir. Surely, sir. I will share with them the PPT, and I request the participants to please go through the PPT. And meanwhile, if you find any queries, you keep those queries in the next sessions. Thank you, sir.
Okay. Thank you very much. I think for today, but we can continue the lecture in the next session tomorrow, isn't it?
Yes, sir. Yes, sir.
Okay.
Tomorrow the session will start from 14 hours IST only.
Okay. Thank you. Then keep in touch, and then thank you. Then have a nice evening. So then see you too. Thank you. Bye bye. Thank you.
Thank you, sir. Thank you. Thank you. Oh, okay, participants. Then we can conclude the